All right, so let's begin by talking about the properties of chiral compounds, and we call chiral compounds optically active. So two different enantiomers are identical except in their interaction with other chiral substances. Okay? Otherwise, they have identical physical properties. So in general, two enantiomers are going to have identical physical properties. Same boiling point, melting point, etc., and so on. Except for how they interact with something called plane-polarized light. So that is light that has an electric vector that oscillates in just a single plane, and it arises from passing ordinary light through, no surprise, a polarizer. And a polarimeter is the instrument that we measure the rotation of plane polarized light in by a compound. Okay, and so that is something that is a cartoon. It looks something like this with achiral compounds. The light that exits the sample tube is unchanged. So the way the sample affects the light, it doesn't affect the plane of polarization of the light. Okay, when the polarization, the plane of the polarized light, is not changed, the compound's optically inactive. And that's something that most, and for our purposes in this class, all achiral compounds are going to do. That is not rotate plane polarized light. With chiral compounds, the plane of the polarized light is rotated. So when light passes through these compounds, the polarized light, and rotates, the compound is optically active. That is a hallmark of chiral compounds. Okay? Chiral compounds rotate plane polarized light. But all their other physical properties, the measured physical properties that they have, are identical. They're identical in every other way. Okay, rotation of plane polarized light can be clockwise or counterclockwise. And if the rotation's clockwise, that compound is called dextrorotatory. And the label we give for that is D or plus. If the rotation of the light coming out of the polarimeter is counterclockwise, we call that compound levorotatory. The rotation is L. I kind of think of that as left for counterclockwise. But it really means levorotatory. L or minus, levorotatory rotation, D or plus, dextrorotatory clockwise rotation of the plane polarized light. Now, that is going to result in two enantiomers. If they're pure, they'll rotate plane polarized light to an equal degree in each of these opposite directions. So an R enantiomer, right, for instance, the R version of the enantiomer may be dextrorotatory. And let's say it rotates the light 32 degrees clockwise. That means that the S enantiomer is going to rotate 32 degrees counterclockwise and be levorotatory. Now R and S don't always correspond to D and L. You can have an R stereoisomer be L or D. You can have an S stereoisomer be L or D, but they'll always be opposite to each other. Okay? So again, as I said, the same concentration and purity of each enantiomer is going to rotate the light to the same magnitude, to the same number of degrees, but with a different sign. Okay? And R and S can be either plus or minus. There's no relationship between the nomenclature RNS and which way the light's rotated, clockwise or counterclockwise. What we call an equal amount of two enantiomers is a racemic mixture or a racemate. So you have 50% R, 50% S of a stereoisomeric compound. You have a racemic mixture, and they cancel each other when you put them in the polarimeter. You have them because you have each enantiomer trying to rotate the light to the same magnitude in opposite directions, so they cancel, and that's why the mixture is optically inactive. So they simply are working against each other and cancel their effects. So overall, no rotations observed. Let's take a look again. This is really important at the properties of enantiomers. Melting point, boiling point, enantiomers, pure enantiomers are different. Identical in every way as far as melting point and boiling point. Same numbers there. Racemic A plus B may be different from A and B individually, okay? But racemic A and B are going to have a zero rotation. They're going to be optically inactive, and the optical rotation of A or B are going to be opposite if they're pure and if they're present in the same concentration. All right, that's a summary of what we discussed on the previous slides, and we measure the degree of this rotation by the chiral compound of the plane polarized light, and it's this simple formula. The observed rotation in degrees is alpha, and that is determined from the length of the sample tube, which is always given, times the concentration of your compound. It all goes in the denominator above, and then you have the observed rotation. So specific rotation equals the observed rotation over the length of the sample tube times the concentration. Okay, and the dm is decimeters. Okay, and G milligrams per mils. And these are temperature dependent. We do these at room temperature, and we do these at a certain wavelength of 589 nanometers. So those are constants. All right, and that's how we can compare the degree of rotation. And this is often reported as a physical property of enantiomers. Okay. Now, how much of one enantiomer is present in excess of another, if there's a mixture, is called enantiomeric excess. And the symbol there, no surprise, is EE, and EE equals the percent of one enantiomer minus the percent of the other enantiomer. So let's say you have 75% of the R and 25% of the S in a mixture. The excess is 50. Okay, I hope that was simple enough math. All right, and there's a 50% excess. The EE is 50%. Okay. And you can also calculate that from the specific rotation, which you get from your polarimeter measurement. That's going to be the, you have to know the specific rotation of your pure enantiomer in order to compare. So you look at your specific rotation of your measured mixture and divide that by the specific rotation of pure enantiomer times 100%. That gives you, and that's another way to determine the enantiomeric excess. Now, diastereomers, their physical properties, this is a different story. So diastereomers are going to have different solubilities, different melting points, different boiling points. Okay, and they're not going to have a DL designation. Here, they're not going to rotate plane polarized light. Okay, so what we see is that, well, I shouldn't say diastereomers won't rotate plane polarized light. It's not true. When one of the diastereomers is a meso compound, of course it won't rotate plane polarized light because it's achiral. So I want you to take a look at this table and notice in compound A, the two stereogenic carbons are RR. Right? Each of those is R. If you do, and you should do, your Kahn-Ingold-Prelog rules, that's what assigning R and S is called. And in B, the two stereogenic centers are both S. Okay, and you can see that A and B are going to be enantiomers because you have an RR and an SS. Okay, that's one way to tell. And that RS, the RS version of those, is going to be a diastereomer of the other two. Okay, think about that. That should make sense. And because C has a superimposable mirror image, because it has a chiral plane, a mirror plane right down its center, the left and right halves are identical. It's achiral, it's not going to rotate light, it's not going to have a specific rotation. But A and B are enantiomers. Same melting point, same boiling point, same solubility, right? C is a diastereomer of each of A and B. And so its melting point or boiling point and solubility and other physical properties are going to be different than A and B. Now, the racemic mixture of A and B is going to have a different melting point than the single enantiomers. So they have the same solubility, but a different melting point and a different specific rotation, namely 0, because they cancel each other. All right, and they don't lose the RS designation. It's just there's half RS and half SR. And we designate that DL. When you see DL together like that, typically it's going to be a diastereomer. And because, again, don't memorize that. All that's telling us is that you're rotating equally to the left and the right. You're rotating the light in both left and right. That shows that you have two enantiomers, okay, and present in your sample. Okay. So diastereomers and constitutional isomers are going to have different physical properties, and they can be separated by common techniques. Okay, enantiomers need to be separated by chiral techniques because they bind to other chiral molecules in a different fashion from each other. Okay, we'll hear more about that as time goes on. But diastereomers can be treated pretty much like distinct compounds. Whereas enantiomers, it's harder for nature to distinguish those from each other with just one chiral center. Okay, enantiomers have the same chemical properties except for reactions and interactions with other chiral species. And that's why drugs are chiral, typically, because guess what? We're all chiral, or almost all except for glycine or amino acids, and therefore proteins are chiral. And so to interact, we need the drugs to be chiral in order for them to be effective, because if you change the stereocenter, if you change the drug interaction's not going to be the same, because again, each of us, we all have chiral proteins, for instance, okay? And so the way that S-ibuprofen would interact with our chiral protein is going to be different than R-ibuprofen, okay? And ibuprofen, as you may know, is the active ingredient in Motrin and Advil. Fluoxetine is an active component in Prozac. Notice Each of these have the one stereogenic center. We drawn them with the wedges and dashes. There's a reason that we use the S version of ibuprofen rather than the R version, and the R version of fluoxetine rather than the S version. Again, they don't work as well, right? Again, because we're chiral. And so that means that different enantiomers or different chiral compounds are going to interact differently with chiral biomolecules. Okay, so the mirror images can be less effective as pharmaceuticals. And here's another sort of striking example. Here's naproxen. You may have heard of that. It's a relatively common anti-inflammatory agent. And look at its mirror image. Its mirror image is toxic to the liver. All right, so that's why you're not going to be sold a racemic mixture of naproxen if you have inflammation, right? You're only going to be given the S-naproxen. So the odors of molecules can actually change due to changing an enantiomer, right? So S-carvone smells like caraway. R-carvone is spearmint. Why would that be? Well, apparently our receptors, our olfactory receptors, are chiral. So they interact with other chiral molecules as if they're different. Because they're chiral, because our receptors are chiral, they can distinguish enantiomers. Okay. So olfactory receptors actually are nerve cells at the top of the nasal passages, and that gives us a nerve impulse that travels to the brain that interprets impulses from the distinct receptors as the odor, as the specific odors. So you see cyclooctane, for instance, bound on an olfactory hair right here, and it fits. It fits in, and if you change the orientation in space of some substituents, the fit wouldn't be quite as good, because again, this cavity is going to be chiral. Now, cyclooctane is not really a chiral molecule. It's just an example here, and this is where it is, and in the airflow, the brain, etc., and so on, and that's how the lining, it reaches the lining of the olfactory bulb in the nasal passage, and then that gets sent as a signal, a nerve signal to the brain. And that's it for Chapter 5. And chirality and everything associated with it is critical to nature. It's critical in this course. So study hard.